Hello everyone, welcome to the next lecture of transistor amplifiers. Again, we are talking about how to use MOSFETs in amplifier circuits. Earlier we talked in very detail about how to use a MOSFET to develop a linear amplifier. We discussed what are the voltage swings that are allowed at the input terminal that will make sure our transistor or the output of the transistor or the amplifier, importantly, will not enter into the cutoff region and or the triode region. We also talked about how to select a quiescent point while making sure that we get a highest voltage gain, allowable swings as well. Um, okay, so we finished our last lecture on developing these equivalent circuit models, and today we're going to see how we can use some of these models to solve different configurations of the amplifier circuits. So here are different configurations of the amplifiers. There are three basic configurations of using a MOSFET as an amplifier. So the common thing about all the three configurations is the first thing that we do is we connect one of those terminals, one of the three terminals, source, ground, or gate, to the ground, and we keep that as a common ground in between input and the output to make a two-port network. So if we do that, we get these three basic configurations of the MOSFET amplifier. Here is a common source. You can see that the source here is grounded, right? And the input is applied in between gate and source, and the output is in between a drain and the source. Similarly, you can see over here, right? The source terminal is grounded and is common to both input and outputs. Similarly, for a common gate configuration, our now gate is directly grounded. Our input is applied at the source terminal, and we have connected this output resistance to convert the transconductance amplifier to the voltage amplifier at the drain terminal. Let's look at the third configuration, a common drain configuration. In a common drain configuration, we have grounded a drain now, our drain terminal, and we have applied the input terminal, the input voltage to the gate terminal, and our output voltage is again at the in between source and the drain terminal. Why this configuration is called as a source follower, we are going to also see that today on why this is called as a source follower. Okay, so let's start with, before we go and analyze the circuits of each one of them, I am going to give you a kind of a recap and more detailed analysis as well on how we can characterize amplifiers. So you have done some of this analysis in the earlier part of the course while doing in chapter number 1 and 2 while discussing the amplifiers and the op-amps as well. So over here, look at the basic configuration over here, right? So assume, right, this is an amplifier equivalent circuit. So what do we have here? We have an input signal to be amplified, the internal resistance of that signal. This is the input voltage that is appearing at the input terminal, the input current to the amplifier, output current from the amplifier, and the resistance at the load. So this is the load resistance at the output. Okay, so we have input terminal, terminal resistance, we have a load resistance connected, and we have also seen that again from earlier part of the course that while developing these amplifiers, we can make a single stage amplifier or these multi-stage cascaded amplifiers in which we have multiple amplifiers connected in series with each other. So when we do that, for example, assume that we have a cascade amplifier in which we have multiple stages of an amplifier, then our V sig for the first stage will be the actual input resistance that we want to amplify. However, for the second stage, it will be the Thevenin output voltage of the preceding stage. Similarly, for the load resistance, in terms of the load resistance, if we have a cascaded amplifier, then the load resistance of the last stage of the amplifier is the actual load resistance. However, the load resistance of the previous stages will be the input resistance of the succeeding stage. So this is what we need to consider when we are developing these cascaded amplifiers or multi-stage amplifiers. Okay, so let's delve more deeper into this amplifier circuit. So we can, if we open up this circuit, that we get something like this, and we have discussed that in earlier part of the course as well, more. So this is Rin is the input resistance of the amplifier, which represents the loading effect, right? So ideally, we want an amplifier to have an infinite resistance, and why is that? So that what is happening over here, for example, what is this resistance Rn doing, right? It is, we have the input voltage that is appearing at the input terminal of the amplifier is being dictated by this Rn resistance. If the Rn is infinite, then all the voltage drop will appear as is. Our Vi will be equals to V sig, right? So if Rn is infinite, our V signal equals Vi. This means that there will be no drop across the resistor and there will be no potential loss of the signal. However, if there is some resistance there, right, so there will be a potential drop and we will get the remaining voltage remaining voltage at the input terminal of the amplifier. So ideally, we want this input resistance of the amplifier to be infinite. This effect is known as a loading effect. So this resistance, you can also call it as an input resistance of the amplifier. Then since this is an amplifier, so we have over here a voltage controlled voltage source where Vi is the voltage, input voltage, right? And this is the voltage source. The voltage of this source is AV naught into Vi. If you want to call it, I don't know, we already have a V naught. So the voltage, I can call it, let's suppose VA. So the VA is equals to AV naught into Vi, right? So it is being controlled by, so it's a voltage controlled voltage source. And AV naught. So what is the AV naught? If you remember AV naught from the earlier lectures, AV naught is the open loop gain. There's no feedback involved over here. However, this is the open loop gain. Open loop gain means that our load resistance is infinite. So this is the gain of the amplifier when the load resistance RL equals infinite. So we are going to talk more about this as well. Okay, so let's look into this more detail, right? So first, what is the value of this resistance Rn? Rn is equals to Vi over Ii. So Vi again is the voltage that is appearing at the terminal, and Ii is the current that is flowing into the amplifier, right? So if we want to find out the value at the input terminal, we can easily use this voltage divider rule, which is represented over here, right? So Vi is, you start with the voltage drop V, input voltage V sig into Rn over Rn plus R sig, right? So this is the input voltage that is appearing at the input of an amplifier. So we are also going to determine the output voltage by using the same voltage divider rule. We can write it over here and then we can do it again. Right, so the output voltage, if we do the voltage divider, it will be AV naught Vi into RL over RL plus R naught. So if we apply the voltage divider rule at the input and the output terminals of the amplifier, so this is what we get. We get this Vi value and V naught. We're going to come back to this thing again. Okay, so by the way, quick thing about this, you're going to come across this terminology unilateral. This amplifier circuit is known as a unilateral because of two things. There is no internal feedback here involved. So this means that the input resistance of the amplifier is completely independent of the load resistance. Just something to remember. If you come across in the problems or the homework problems or the exams. Okay, so let's come back to this open circuit voltage gain, right? So this is what we define. The open circuit voltage gain is defined while taking when the load resistance is infinite, right? So it is an output over input when the load resistance is considered infinite. So we have open circuit voltage gain will be the output voltage to the input voltage at load resistance equals infinite. So let's look at this. What is this R naught? So the resistance, this output resistance is the resistance that we can found by looking at the output terminal, by looking inside the amplifier circuit from the output terminal. And if you want to find out the exact value, you can set the VI set to 0. And when you look at the again inside from the output terminal of an amplifier, right? So if you look here, the resistance you're going to come across is the output resistance, which over here is represented by R0, right? So you can also show this thing, the similar thing, by a very simple circuit over here. Input voltage is set to 0. Now you are looking inside the output terminal of an amplifier. So the resistance that you're going to come across will be R0. From this simplified model, we can see that our R0 over here equals to Vx over Ix. Okay, so let's come back to solve. We wanted to solve the voltage gain of an amplifier and the overall voltage gain of an amplifier. And we need to define these terms very specifically here so you understand the basic difference in between these terms. So one term is the open circuit voltage gain that we defined here. So this is the voltage gain of an amplifier when the load resistance is infinite. Okay, so the second voltage gain now we are going to define is the voltage gain of an amplifier, not an open voltage gain, a voltage gain of an amplifier, which means that I'm interested in finding out what is the value of V0 over Vi, right? So we have a V0 output voltage that is appearing at the output of a output terminal of an amplifier, and then we have an input voltage that is appearing at the input terminal of an amplifier, right? So the voltage gain of an amplifier itself is the voltage that is appearing at the input and the output of the amplifier, right? We are going to define another voltage gain which we are going to call as an overall voltage gain. That will has to do with the output voltage versus or divided by the input voltage, that the signal that we wanted to actually amplify. Input signal applied to the amplified circuit. Okay, so we have by now we have two equations. One equation is this, at the input we have this Vi, and the second equation is over here. We have this V0 over here, right? Over here our V0, we can find this V0 by a voltage divider circuit, which is AV0 Vi into RL over RL plus R0 over here. So now just by looking over here, right, so this V0 is the output voltage at an amplifier and this Vi is the input voltage of an amplifier. So just by using this equation I can find this voltage gain V0 over Vi. So if you will do this V0 over Vi, you can find out AV0 into RL over RL plus R0. So this is the voltage gain of an amplifier. You can also find out the same equations over here. Again, this is the voltage divider. By using a voltage divider rule, you can find out the output voltage. And similarly, see, you can take this Vi over here, and this is the value that you're going to get. So this is the voltage gain of an amplifier. Now let's define the other voltage gain that we are interested in. So this is the voltage gain of an amplifier. This is the output, this is the input to the amplifier. However, due to this loading effect, due to the input resistance, the signal resistance, I am more interested in finding out what is the overall voltage gain? What is the voltage gain of the input signal that I will apply, right? So for me, I'm going to define this as the overall voltage gain with the value GV. So what GV will be? GV will be the output voltage that gets amplified to the signal voltage. This was our actual input voltage that we were interested in amplifying, which we are denoting over here with a V signal. And V0 is the output voltage of the amplifier circuit. Okay, so using this, we can define this overall voltage gain. So so let's define this overall voltage gain. Now we have V0 and we have Vsig. So the two equations that we have derived by now, one equation is this again, which is the voltage divider at the input and the voltage divider rule at the output. So we had these two equations. So one is the voltage gain and other one is this input voltage. Now over here, I can see that I have a V0 and I need a Vsig. So over here, for example, V0 over V signal, I have, where is V0? So V0 value is over here, right? So V0 is, or I can put this value of the Vsig over here, right? So our V0 will become RL over RL plus R0 into AV0 into VI. No, actually, no. It should be, yes, into VI. VI will be equal to Rn over Rn plus R sig into multiplied by V sig. So if we take this V sig all the way over here on the other side, then we can get this equation as our overall voltage gain. So our overall voltage gain will be RL over RL plus R naught into the open loop voltage gain into Rn over Rn plus R signal value. So this is another voltage gain that needs to be remembered, kind of an overall voltage gain. So two important things that we're gonna come back in terms of equations that are important. One is this voltage gain of an amplifier, and other is the overall voltage gain. And we will come back to these equations again. Okay, so by now we started with this thing that here are the three basic configurations. We can use the MOSFET as an amplifier in these three basic configuration as a common source, common gate, and a common drain. We started with a kind of a very generic representation of an amplifier and ended up deriving these equations for a open loop voltage gain of an amplifier V naught over Vi, and the overall voltage gain of the amplifier circuit V naught over V sig. Now let's look at the three different configurations. Let's look at all three of them one by one. So let's start with a common source amplifier. Okay, so here is a common source amplifier. As we have earlier seen, our source is grounded, right? Our source is grounded. We are applying the input voltage to the gate terminal, and here is the output that we are collecting. Okay, now if using the equivalent circuit models, when we have a common source, if I will go back to these equivalent models, when I have a common source here, I can easily use this equivalent circuit model to open up that amplifier circuit, right? So so I can represent that with the with that equivalent circuit, with this equivalent circuit over here. All right, so let's go. Okay, so let's open this up. We have input signal, the internal resistance. Then we have input voltage Vi. This is the input voltage to the amplifier, and this voltage is essentially the gate to source voltage, the input voltage in between the gate and the source terminal, right? Then we have an ID, the drain current, which is equals to GMVGS. We have seen that while developing these equivalent circuit models. And then at the output we have a RD, and we are taking an output across this resistor. So some of the important things that you can realize over here in this circuit is, since input is applied at the gate terminal, and we know that while operating the transistor in the saturation region, the gate current that flows into the amplifier will be equals to 0, right? So since our gate current is equal to 0, this means that the input resistance will be equals to infinite. So the input resistance that can be seen at the inside, while looking inside at the input terminal of the device, will be equals to infinite, because the gate current is infinite. So input resistance over here will be infinite as well. Okay, so if the so interesting thing over here, right? So if our input resistance is infinite because our gate current was 0, so this means that there will be no loading effect. This means that our input voltage, our signal voltage that will apply, it will appear as is over here at the input of an amplifier. So this means that our V sig will be equal to Vi will be equals to VGS. Okay, and then our output resistance, it can be very easily seen over here. For the output resistance, when I look into the transistor from the output terminal, the resistance that I do see is this value of RD. So that is why my output resistance equals RD. Okay, so let's analyze the circuit. So while analyzing the circuit, we have to determine all of these values. So our Rn is infinite. We already determined that because our gate current was equals to 0. So input resistance will be infinite. This means that our input voltage will be equals to the signal voltage, right? And why is that? Because again, resistance is infinite, so there will be no loading effect. And since our input voltage is equal to the gate to source voltage here, which is the gate to source voltage that we apply in between the gate and source terminal. So our input voltage, gate to source voltage, and signal voltage, all three of them will be equals to 0, right? So Vi equals V6 equals VGS. Okay, so now let's determine the value of V naught. In order to determine the value of the V naught in this configuration, we have already kind of did this calculations earlier. Let me go back to the slide. Right, okay, over here, right? So this is the voltage gain or the value that we find out. So this VDS is our output voltage. So this is the voltage that is appearing in between drain and the source, right? Going back here. Let's look here just to confirm again, right? So this is the voltage that is appearing in between, right? So our output voltage is the voltage that is appearing in between so this is our drain terminal and this is our source terminal, in between drain and the source. So in between drain and the source, what is the value here? So VDS equals V naught. So our V naught equals minus GM RD VGS. So this is the value of V naught. Okay, so our input resistance is infinite, input voltage is V6, VGS equals VI, and output voltage is minus GM VGS into RD. Okay, so once we find out this value of the V naught as well, our next step is to find out what is the value of the open circuit voltage gain. Our open circuit voltage gain is when the load resistance is infinite. We haven't connected a load here, so our V naught will be equals to V naught again is the voltage that is appearing over here, and Vi is what is appearing over here. So when no voltage is connected, so this means that I can simply drive it from here, right? So V naught over VGS equals minus GM into RD. So our open circuit voltage gain will be can be easily find out from this. Now let's look at how to find the voltage gain of an amplifier and the overall voltage gain of an amplifier. So we're going to use the same equations. Our voltage gain of an amplifier is over here. AV equals V naught over VI, AV naught RL plus R naught. Right, so AV naught RL plus R naught. Right, so we have AV naught RL over RL plus R naught. So this is the overall voltage gain. So our AV naught is minus GMRD, RL over RL plus R naught, value is RD, right? Our load resistor appears in parallel to the, our load resistor is going to appear in parallel over here to the RD. So this is the voltage gain that we ended up finding, right? So R naught equals to RD, and this is the value of the voltage gain that we ended up finding. You can easily see that over here, RD into RL over RL plus RD, the RL and RD resistances are appearing in parallel. Similarly, in order to find the overall voltage gain, we can use the same equation. No, actually we cannot, because we have an input resistance over here. However, in this case, our input resistance was infinite. If our input resistance is infinite, right, this means that there is no loading effect, right? So if our input resistance is infinite, this means that my V sig equals Vi. And if that is true, then our initial voltage gain was V naught over Vi, and our GV was V naught over V sig. If both of them are equal, this means that our voltage gain and the overall voltage gain are the similar, right? So this is also equals to GV. Right, so V naught over V sig, right, so our overall voltage gain will be equals to the voltage gain of an amplifier. Okay, now let's do the second configuration, we call as a common gate amplifier. Now, okay, so let's look at this simple circuit first, and then we're going to expand this thing. So our gate is grounded. This is our input signal that we have applied. We have an internal resistance. This is the resistance. Again, input resistance is the resistance that is seen while looking into the input terminal of the amplifier, or over here the transistor. This is the input voltage at the input terminal, right, of this. And over here, this is our output voltage, and here's an output resistance, which can be seen looking into the output terminal. Now, How we can expand this? We have a common gate configuration over here. If I will go back to the circuits, right, this were our equivalent circuits. Where is our common gate, right? So I can this is my common gate configuration in between drain and the source and the gate and the source. So it can be a common gate configuration. So I'm going to use this configuration in which we can replace this drain with a current source, and we can connect a resistor in between the gate and the source terminal. Okay. So I'm gonna yeah, okay, so sorry. All right, so let's expand this expand the circuits into an equivalent circuit model. Again, our gate is grounded, so I ended up connecting this drain terminal. Going back to the circuit again, you can see that we have a current source connected to the drain, which is GM VGS, and we have a resistance connected to the source, 1 over GM. Right, so I ended up doing exactly the same thing over here. We have a drain and we have a current source that is connected. The value is I. We are going to determine this value. And then we have a resistance, 1 over GM resistance, that is connected to at the source terminal. Right, okay, so again, if you will look at the output resistance, that is seen by looking at the output terminal, looking into the output terminal of the amplifier or of the transistor over here, you can see that our output resistance is equals to RD. However, when you look inside the input terminal, our input resistances, we are seeing this resistance as an input. So our input resistance now is not infinite, but equals to 1 over GM. So let's determine all the values now, right? So our so let's start with the input resistance. Our input resistance is equals to 1 over GM that we have seen. Okay, so let's find out the value of the V naught. Considering the potential drop across the V naught is represented as this plus minus V naught, and looking at the direction of the current, the V naught over here will be equals to minus I. This is the current that is flowing into RD. So this will be equal to the V naught. Similarly, I can also find the value of, now let us find this value, the value that is flowing into the source terminal, current I. Right, again looking at the potential drop, the VI and the direction of the current. So this current can be written as minus VI over resistance, and the resistance over here is 1 over GM. So I can put down this value over here. So our V naught will become equal to minus I. So it will be VI over 1 over GM into RD. So V naught over VI equals GM into RD. Okay, so this is again the voltage gain of an amplifier. So this is the value of the V naught minus I into RD that we find over here. Then this is the value at the source that we ended up finding over here. And we ended up finding again the open loop voltage gain, right? So because no load resistance is connected, so this was potentially the open loop voltage gain of an amplifier. Okay, so similarly, if we have to find now the overall voltage gain of an amplifier, we can also find similarly the voltage gain of an amplifier as well, which was AV naught into RL over RL plus R naught, and AV naught is again GMRD into RL plus R naught is RD, so it will be GMRD in parallel with RL. Okay, now let's find out the value of the overall voltage gain. Here's the equation of the overall voltage gain. It needs a value of the open loop voltage gain, the load resistance, the output resistance, and the input resistance. Okay, so I already know the value of the input resistance is 1 over GM. Okay, so this is the value of the open loop voltage gain that comes over here. Input resistance is 1 over GM. We already have a value of R6, which will be some value here, and I can replace this R naught by RD. So this will be our value of the overall voltage gain, right? Yeah. Essentially, again, both of these resistances are appearing in parallel, as we can see over here too, in finding the voltage gain of an amplifier before finding the overall voltage gain. Okay, Now let's look at the third configuration. Third configuration is our common drain configuration. Okay, again, looking at the both circuits, we're going to start with a simple A1. Common drain. Now drain is common. We are giving the input voltage to the gate, right? Input voltage, input signal resistance, input potential drop across here, Rn. We know that whenever it is applied to the gate, Ig equals 0, Rn equals infinite. All right. Then again, our R0 is the resistance looking into the source terminal. And then we have a load resistance connected and the output voltage over here. So importantly, again, if you look closely over here, this is essentially going to give you the same configuration as we have used earlier in terms of equivalent circuit models. I can replace this drain terminal with something like this, a constant current source with a value I, and then I can replace this terminal, the source terminal, with a value of the resistance, which is 1 over GM. Right, okay. So the R0, so the resistance, our output resistance is the resistance looking into the output terminal of the amplifier. So when I look into the output terminal of an amplifier, the resistance that I see is 1 over GM. So this is the output resistance now, and the input resistance is infinite, right? Because the gate current is 0. All right, so let's solve this circuit now. Okay, so we ended up finding the value of the Rn, that is infinite, R0, 1 over GM. Let's find the value of the voltage gain. All right, so our AV, we know that AV is equal to V0 over VI. And V0 is, our AV is V0 over VI, which is equals to AV0 into RL over RL plus R0. Let me cross check here. All right, so our AV is AV0 into RL over RL plus R0. All right, here, right? So our AV is AV0 RL over RL plus R0. We know that what is our R0? R0 is 1 over GM. Let's find out the value of AV0. So what is the value of the AV0? We know that AV0 is the value of the voltage gain when the load resistance is infinite, right? Now, interesting thing, now look over here very closely, that when this load resistance is infinite, this will become an open circuit. Then whatever the value that is appearing over here, the same value is going to appear over here. When RL will become infinite, the V0 starts to follow the input voltage VI, right? So that is why it is called as a source follower too. So our AV0 at RL equals to infinity equals to 1, right? Okay. So now we can replace this value of 1 over here and we can get down to this equation. Okay, this is the same thing as here. So we ended up replacing this value R0 with 1 over GM. Similarly, over here, we can find out the value of the overall voltage gain as well. We know that since, okay, so actually interestingly, since our input resistance is infinite, so this means that our signal voltage is will also be equals to the input voltage. And we know that when the signal voltage is equal to the input voltage, our overall voltage gain is equal to the voltage gain of an amplifier. So our overall voltage gain will be exactly similar over here as well, which will be RL over RL plus 1 over GM. Okay, so this is the overall voltage gain. So a couple of quick things over here, right? So because we know that the value of the GM is usually very low, so 1 over GM value is usually low, the voltage gain that we will get from this circuit or from this configuration is very close to unity. And that is why this is known as a source follower, because the voltage at the source terminal is going to follow that at the input. So whatever the voltage that we apply at the input, considering this voltage, this drop to be very, very small, whatever is considering the 1 over GM drop to be very small, whatever the voltage that we apply at the input, since input resistance is infinite, so VI, it is our output will follow the same voltage levels. Our gain is very close to unity. So we can use this configuration to develop the source followers as well. Okay, so this is where we will end our lecture today. In our today's lecture, we talked about different, again, configurations in which we can use an NMOS or a MOS transistor to develop amplifier circuits. We discussed common drain, common source, and common gate amplifier. Importantly, we derived all of these expressions of the voltage gain of an amplifier, open loop voltage gain, overall voltage gain. Importantly, before determining any of these voltage gains, some of the things that are important is to see what is the input resistance, what is the output resistance. And when you determine the input and the output resistance, you can find out what will be the VI value, right? Whether there will be any loading effect or not. So that will dictate whether the overall voltage gain will be equal to the amplifier voltage gains or not. So I hope that doing these three analyses, you should be able to solve any of the circuits or in any of the configurations. In the next lecture, I will do a few quick examples so that we can also delve more deeper into solving some of the circuits. And then that will be the final lecture on this MOS FET amplifiers topic. And beyond that, we will start to talk about our next topic, bipolar junction transistors. Okay, so with that, thank you so much. And I will talk to you next time. All right, bye-bye.